way to route packets is called flooding, and that's an easy way to send a packet to all the routers. So when we do flooding, every incoming packet is sent out on every outgoing line. The advantage of this method is that even if there is a large number of routers that are not working, then, for example, there is a war and the routers, a lot of the routers were destroyed. Even if that's the case, flooding will find a path to the destination. If the path exists, it will find it. So even large number of routers do not function, the flooding, we will find a path. If one exists. The routers only need to know their neighbors. Now, of course, the flooding will generate a vast number of duplicate packets, or even an infinite number of duplicate packets. So if that happens, we need some way to damp the process and stop these infinite packets. So there needs to be some measure has to be taken to get rid of all these duplicate packets. So one way to do that, there's many ways to do that, but each hop can keep a counter and keep decrementing the counter on this packet as it circulates around, and eventually when the counter hits 0, then the packet can be discarded. This flooding is used in some wireless networks to find all the devices that are in range. So, one algorithm we looked at was the Dijkstra shortest path, and now we will look at another routing algorithm called distance vector routing. With this algorithm, each router maintains a table or a vector that is showing the distance to the best known distance to each destination, and so destinations is A, B, C, D, E, F, G, K, L, and for each one of these, on which line it should forward the packet. So if the packet is going to F, then it delay to these that it will take to get to these routers. The way this table is maintained is by receiving information from all of the neighbors of J. So these are called vectors. Vector for J from its neighbor A. The neighbor A will tell its delays that it knows to all of these other routers. The neighbor I will tell its delays to all these routers. Neighbor A should tell its delays to all the routers, and so on. So our router J can use this to compute the best delay that it knows for each destination router. These are being updated about every 10 seconds. So if anything changes in the delays, the neighbors will know about it immediately, and they will recompute its routing table and refresh it. So the distance vector router, each router maintains a table or a vector giving the best known distance to each destination. This table is updated by exchanging information with the neighbors. And eventually every router knows the best link to reach each destination. So for each line in the table, there are two parts. The preferred outgoing line was this right here, the outgoing line, and the estimated distance or delay to that destination. And the router knows the delay to all of its neighbors. So once it receives the distance vectors, it can perform a calculation based on its neighbors to determine, to find which estimate is the best, and use that for the corresponding link in its routing table. Now this distance vector is good for collective computing of the shortest path for the entire network. However, it has one issue if called count to infinity, because its drawback is that it reacts rapidly to good news. So it's getting refreshed distance vectors from all its neighbors every 10 seconds, and if anything changes, then it knows about it. But it's very slow to react to bad news. So for example, if on the next exchange of the distance vectors, one of the routers A suddenly reports a short delay to another router X, then that's good, but we can switch to the new router immediately. But if A is down initially, then it is very slow to propagate once it comes back up. So it's going to take there.